now to the next session, and that's a session on data challenges and opportunities. And this session will be led by Roel Wuits, and Roel is manager of the Exascience Life Lab at IMEC, and also Professor at the KU Leuven, and Roel was also one of the work package leads within ATHENA. So please, Roel.
So indeed, another block now on data challenges and opportunities, which was one of the things we of course needed to tackle in Project ATHENA. And so we all know, we've heard already many examples in other talks, but there is a lot of data available. There is a lot of data available in a hospital, also outside, so that spans data that is in patient records about the history of patients, health practitioners, there can be insurance data, there can be data from wearables, many data that are available that can characterize individual patient, that can help a doctor in order to make treatment decisions. So that means that we can use this data in, for example, machine learning. I do not like the term AI. It's not artificial, well, maybe. It's certainly not intelligence. So I much prefer machine learning. Yeah? So you can have decision support systems. You can have machine learning in order to look at patterns that are available in all of this data that's becoming available. But of course, there is more than having that in a single place. It actually spans multiple places. We've seen examples that can span multiple hospitals, that can also span hospitals and external parties. So the question is, can we make use of all of that data? And here in work package 3, where we worked a lot, there was like how to enable this, and we'll have another session on what kind of analytics you can do, but that I will not discuss. So we have all this data available, it spans this, it can span within a single place or a smaller region. It goes actually wider, so even within a hospital that can already be challenging, because even there you have multiple silos. But we can see that for the whole of Flanders, we can see that for the whole of Belgium, we can see that for the whole of Europe, we can see that for worldwide. And some of the patterns that we like to see, think about rare diseases, actually only make sense if we look at them in a much broader context. But of course, I do not have to tell you all day, we've already been looking at that. There is a lot of challenges if you want to do that. We saw a lot of potential opportunities, but there is still many challenges. That can be legislative, and I think we first had already a lot of talk about that in the previous session. There can be cultural differences, there can be medical differences, ethical, there can be technological differences and challenges. And so I will not talk about solutions. I was only here in order to sketch you this picture. But it's my great pleasure to introduce you two people that are actually able to talk about their experiences and their solutions. And in this session, we'll have two speakers. Michel van Spijphoek, who is Director of Data Sciences in Janssen Pharmaceutica, already the past 7 years. And so he is the driving force behind the Honneur and the Federate approaches, so to bring clinical and data sciences together. I have a cheat sheet, so I cannot lie. So he will talk about challenges and solutions for privacy-preserving data reuse in research. And afterwards, well, there might be differences between how we do this in ATHENA or in Flanders or in Belgium with how we do this in the Netherlands, of course also worldwide. And therefore, we also invited a second speaker, Professor Dr. André Dekker, who is Professor of Clinical Data Science at Maastricht University and at the Maastro Clinic. And so he will talk about federated learning again, but how this is done, or his experience with doing this in the Netherlands. And that way we can see differences and commonalities, what can we learn, maybe where we can strengthen each other. So good, so I first will give the floor to Michel, and then afterwards, of course, to André.
Thank you, Roel. Hello, everyone. So I will try to explain you mainly two things. I will try to explain you how the things that we're doing in setting up federated data networks and trying to make that work, how that's not so much a technical problem, but actually has way other dimensions. The second thing I will try to explain you is that we don't have a big data problem. We wish we would have one. We want to create a big data problem, but our main problem is mainly that we have very few data on very few subjects. Maybe we have lots of data points, but that doesn't make it a big data problem. So actually, to talk what to my opinions are the keys to be successful. It starts at the bottom. It's trust and willingness. And for all respect, we can create contracts as much as we want, and they are needed and so on. We need technical infrastructure, but it starts and ends with actually the relationship, the trust, the knowledge, the collaboration between individual partners, between humans. That's the core. The second thing, important, as Deming once said, in God we trust and all the rest is data. Good data are the cornerstone of actually making this thing work. And we have a couple of good examples. We have a couple of learnings to take along, but that's a very important second aspect. The third aspect is actually on the knowledge, understanding the data as well, let's say on the source, as the people who actually do the conversion to that common data model. You need to have that expertise, it's critical. And the fourth pillar is actually what Danny also referred to, is actually the analysis method, to have those robust, repeatable, and so on. But that's the cherry on the cake. So you might have seen this is a publication that we published together with some other people on Eden, actually on the different steps that are taking place actually when you convert data to the OMOP common data model. So the standard process from starting off to summarizing to creating the ETL and so on, with an indication of actually the throughput times. The idealized process, I would almost say, but you already see that it's not a walk in the park. It's indeed, like Frank mentioned, it's a marathon. I would even say it's a long marathon, but okay. And what are some of the assumptions that we typically make when we're engaging in an exercise like that? We actually sometimes perceive technology as a substitute of trust. It's something that we need to add on top of that can enforce certain things, but it doesn't replace. If we don't trust each other, we will also not trust the technology that underpins it. We also typically, and now I'm talking about the content, we always have the impression that if we have large, big data and so on in a very advanced database that is of higher quality than something that is, let's say, in Excel or whatever it happens to be. That's not always necessary. You can have big or large volumes of data of mediocre quality, while you can have good quality data in a small repository. That's quite well possible, and we've seen cases of that. It's also not possible to get to good quality, to good data quality with just applying technology. Bad data stays bad no matter what you do with it. And the fourth fallacy is, I think, an important one that we see in different institutions, in different collaborations. We see it in our organization, we see it everywhere. We always assume that we can make all this work just by having enough meetings around it. That's not, it's a tremendous amount of work to actually make it happen. And it's actually by the contribution of individuals who actually make it happen that it's truly been done, not by organizing meetings. I have a certain, yeah, anyhow. So, now coming back to where we are. So despite actually, well, I think we are following the rules of the game on how it should be done. We see that the throughput times for converting that to the OMOP common data model varies anywhere between 6 months and 2 years. We see that in this project, we see that also in others. There's actually also, from a content perspective, even if you're in the same discipline, and Frank also mentioned it, sometimes a very limited overlap in actually how and which variables you capture between different institutions. For the more complex variables, and Jolien will be able to confirm that, for instance, a treatment line in multiple myeloma, we can spend weeks, if not months, to come to the right logic to convert it correctly. And last but not least, there is indeed a certain challenge in actually incorporating different types of data, like omics data into our common data model. Not so much purely on a technical level, but purely in terms of coordination and basically being able to link it correctly and so on. That's some of the challenges. So where are we with the mapping? So basically we have four sites actually that we have, let's say, up and running. So of course here UZ Leuven, who is active in the multiple myeloma space in the bladder cancer, and actually also as part of that integrated omics data. We have Zol, who is actually in the bladder cancer, Siège Liège with the multiple myeloma data, and OLV Aalst also on the bladder cancer. So, and once we've done through that exercise, we can indeed, on the one hand, create a summary level data, so aggregate statistics, which is extremely important when we then come to ask our research questions, that we can know where we can find which variable or what kind of questions we are truly indeed able to ask. And I've made some screenshots on the one hand from multiple myeloma and on the other hand from bladder cancer. Now, I've made some comments, but also want to point out some things that, to my opinion, indeed do work. Or some best practices. So it's extremely important to do the proper, what I call due diligence. So it's important to actually assess the completeness of the data. And that doesn't mean, the context is extremely important because we're looking at longitudinal things. So dates is extremely important to have that associated with every single point. Equally important is that the harmonization, OMOP harmonization, we sometimes think, okay, yeah, so OMOP, it's a common data model, so you just do it and then you're done. No, in every disease, you really need to coordinate and make sure that you have consistency in the way that you map those things, because otherwise you will have the divergence in your analysis capabilities. I already mentioned, it's quite keen to me to have knowledgeable people participating and contributing. And the last bullet is something that you cannot do without, is what I would call an IT organization that is really contributing and cooperating in this process. But the most important factor, I already mentioned it, is really the people that make it happen. So, and to save some time, I will not read all the names, but thank you all for your contribution. Now, the platform, it has been mentioned a couple of times, is basically the underpinning where we actually then perform the federated analysis is the Federate platform. So that's a data management and analysis platform. And you see here a bit how it's structured. So that's really the central piece, with the portal containing the core functionality. So on the one hand, it contains a data catalog to see the different data sets, descriptive, what's in there. You actually have the study catalog where you can define the individual research questions and then come to execute them. We have and you saw a snapshot of that. We have the data set profiler, which gives you the univariate statistics that you know which variable is present where. And then we also have the concept browser, which is very equivalent. You can search on a particular term, a particular variable, whether it's a measurement, whether it's a drug concept, a condition, and you can see where in the network it's available. The basic mechanism, if you haven't seen our animated PowerPoint slide, it's the highlight actually of the thing. Oh, and sorry, there is still on Earth, but it should read ATHENA. But basically, the right-hand side is the central part, and then on the left-hand side we have the individual nodes. we have the individual nodes. So how does it work? So you define centrally a script, an analysis, that actually gets transferred or pulled by the individual site. So it's not that you can trigger the execution, it really needs to be pulled. Then that script there gets replicated at the individual site. They perform their analysis, and they actually then send the result back, and you do a meta-analysis or a summary analysis on those data. So that's one method. That's the predominant method. That's also what Danny described. Now, and that's also what you see here. So you basically dispatch the same analysis to the different sites. There's also another way that you can do it, which is federated one-shot analysis. So basically what you do is you send one request to each participant, and then centrally you calculate a result out of that. So for instance, if you want to take a population mean over your entire network, you do something different than asking everybody to send their mean. And then the last thing is actually a federated analysis with iteration. So what that is you send first a request to one center, which actually trains. It sends back some parameters. Those parameters are then actually fed to a second node who will perform an analysis, or will use that as input, and then it goes through the third one. And so you get into an iterative cycle until you actually get a result. For instance, a distributed Cox proportional hazard regression, although you could also do that as a one-shot, but that's one possibility. The last thing I want to mention is, I think, and it has been mentioned by Frank and also by Michel, is we also try to actually lower down the hurdle to actually perform analysis. So instead of trying to make it more complex, we really want to give people with the medical knowledge the capability to look at their own data. And so that's what we call that disease trajectory analysis. And it's basically underlying, it's using the OMOP data and transforms the data into what we call a clinical event model, on which you then can do the routine standard analysis and slice and dice your data. All right, yeah, so yeah, survival curves or the Cox proportional hazard regression, that kind of things. So in conclusion, where are we? We have indeed the ability to run distributed and federated analytics. We still need to complete the validation actually on the OMOP data. So although we've mapped now everyone, we still have validation work to be done. But there is a significant improvement opportunity to further improve that process for getting that readiness and completeness of the map data. And the challenge is not actually in the sophistication of your, sorry for those who come after me, on the sophistication of your analytical algorithms. It's about the data, get the data right, that's what matters. And obviously we all learned a lot about how different data can be around different institutions. Thank you.
So this is always a risky presentation, right? To come from the Netherlands and ask you Belgians how it's done. And I won't do that. I'll be more humble, hopefully, than normally. Because the previous presentation basically described very well, I think, how to do this. I will share my experience or our experience from up north, doing federated learning, and I'll touch on some of the subjects that were discussed before. I do have one disclosure, which is that we have a spin-out company called Medical Data Works, in which we do this kind of thing, and we are involved in that. Okay, so my department at Maastricht University and the medical center there consists of about 50 people. And one of our, the top one you see, one of our goals is to develop fair, federated health data sharing infrastructures. Then we do machine learning. As was said, we don't do very fancy machine learning. We're much more focused on the data because that determines indeed the result. And we do work in a number of diseases. So why did we start with federated learning? It's always good to understand why you do things before you start doing something. So I'll tell you our rationale. And our rationale was very simple. We asked an oncologist at Maastricht Clinic, so a clinic where I get paid, to predict 2-year survival in lung cancer patients. So we basically asked our physicians, you've seen these lung cancer patients at intake, you know the treatment that you're going to give. Now give us a percentage or probability that these patients will be alive 2 years from now. And so you can make an ordering experiment like that, because some patients are very likely to survive according to their doctor, and some patients are less likely to survive. And when you then, after 2 years, get an answer to that question, because you know who's alive and dead after 2 years, you can put a number on the quality of that individual prediction. And in machine learning, that's called error in the curve. So 1 is a perfect predictor. You can see the doctor has put all the patients that have survived, he or she has assigned a high probability to those patients because they're on the right, and and all the deceased patients are on the left. And then the doctor has an error in the curve of 1, so he or she is a perfect predictor of outcome. Right? If the doctor is random, it would look like the bottom. Right? You see that the prediction of the doctor didn't mean anything for the actual survival. And 0.72 you see in the middle. You see some good predictions, but also some errors. I'm telling you this because this is a hard exercise for doctors. The doctors in Maastricht have an error in the curve of 0.56. And if you put a confidence interval on that, these were 5 doctors, 20 years of experience, some with no experience, didn't matter, same problem. The confidence interval had included 0.5. That means if you come into my clinic with lung cancer and you ask to our oncologist, will I be dead or alive 2 years from now? The answer that you get is just as good as tossing a coin. And that's not because we are such bad doctors in Maastricht. It is being repeated all over the world, this problem. This is something that we talked about in 2006. So this research started about 17 years ago, when we said we have to address the situation, and apparently doctors are humans that cannot predict such future outcomes. We think data can predict that. We need to go to a learning healthcare system which we use the data of these patients to start predicting these outcomes. Because if we can't predict an outcome of a treatment, we cannot advise our patients which treatment is better. That is the problem that we are facing, the unpredictability of healthcare. So you need a lot of data for that, and we realized already very quickly that Maastricht is too small. Well, if we want to do such machine learning or data mining or whatever it wasn't called AI at that time, we needed data from other sites. And there are about 100,000 hospitals in the world. So how can we get data from 100,000 hospitals, we asked ourselves. And what will not happen is that all these parties will send their data to Maastricht. We discovered this very early, right? So we send them an Excel sheet and said, fill in all your data, patient data, and send it to Maastricht. They said no, right? And it wasn't due to GDPR, but because it didn't exist at that time, right? This is 2006. They said no before, the first thing they said, it just takes too much time to fill in your Excel sheet, Andre. I don't have the time for that. The second thing they'd say is, I don't want you to have my data. I want to publish on my own data. I'm worried, especially the American sites were saying, I'm worried that you find out I'm doing something wrong and then I'm sued or in the paper. Right? Then people said, especially when GDPR came, I'm not allowed to. GDPR, HIPAA. Right? If people say that, they mean 1 and 2. Right? Because on the GDPR, as was explained very clearly by our 2 legal scholars, it is very doable to share data. You may need to pseudonymize, you may need a data transfer, you may need to ask for consent. What I didn't like is that you mixed informed consent, which is a clinical trial problem, where you can harm patients. It's a GCP concept, right? It was installed because of the World War II, right? And Declaration of Helsinki, to make sure that patients in trials didn't get physical harm. By using the term informed consent in the GDPR, we're mixing up stuff. And this is confusing doctors all over the world, because they now think they have to get informed consent for data sharing. That is not true. GDPR asks for consent, which may be explicit, specific, informed, free will, but it's not the same as informed consent. And so we should really not talk about informed consent, because it's a different concept. Right? And I don't like that people are mixing it. Technically, it's very easy to share data. That's not the issue. So we said there, I mean, if these troubles are there in the world, we should find a different way. And so federated learning was our solution at that time. We said, if sharing is such a problem, then don't. Find a way where, rather than bringing the mountain to Muhammad will go to the mountain, right? Rather than bringing all the data to the research in Maastricht will go to the data. And so that meant a lot of traveling in the beginning. Right? We sent our PhD students literally to those sites to analyze data, but that doesn't scale. So we needed a situation where we can put a research question in a box and send it somewhere else, right, without the people attached to it. But that research box, and we call it a train. So the train is the research question. If that train comes into Shanghai and Shanghai double clicks on that train, on that application, they need to make sure that it's safe, it doesn't steal their data, it adheres to the Chinese privacy regulations, which are different from ours. And so there has to be track. And track is our metaphor for the legal and the technical governance structure that we need. But then you're still not done. Because as I was explaining just now, if I send a train from Maastricht to Shanghai, that train doesn't speak Chinese. And so the data in China has to be in a state where it is coded, captured in context, the same as the data in Maastricht. And that's nowadays called FAIR data. Right? So we call it FAIR data stations. So every hospital is a station. A train with the question will travel to those stations, and the track is there to make sure it all works, both compliant and technically works. That is the metaphor of the personal health train. So a short history of this is, we described this the first a year later, after we found out that our doctors couldn't predict. We said this sentence in our grant application. The CAT project will use data from distributed databases in multiple clinical data centers, or multiple clinical centers, to develop and validate patient-specific prediction models. So in the beginning, this was hard, and we worked with Siemens a lot on the EuroCAT project. We had grant proposals that were rejected all the time, because they thought it was a stupid idea which will never work. And it took us a long while to get our ministry, the Minister of Health in the Netherlands in 2018, finally wrote, and this is Dutch, but you can see the personal health train in his letter to Parliament, so he's slowly getting somewhere. And then we got 17 million or 69 million euros to organize it. And this is called Health RI, the Health Research Infrastructure. And one of the sustainable fair data, backbone for health-related data, is this number 2, transition to federated data infrastructure. So we now got the money to finally do this. We got the awards. And it's also the personal health thing you can see somewhere on the map of the health ministry. So we at least got to that point where this is now accepted as being an important part of the game. And we started with you guys, with Hasselt and Liège, amongst others. And as was described, what we're doing in federated learning, so don't have to describe it again, is we learn a model locally from data. This is a machine learning model that can separate, for instance, the deceased patients from the alive patients. If Hasselt would do it, it would be the blue line. If Liège would do it, it would be the green line. Maastricht had very different patients, so it said, no, it has to be the purple line, and Eindhoven and Aachen thought differently. And what you share with each other is not those individual data points, but the lines. And the lines are anonymous data. You can prove that these things are anonymous. And therefore, there's no data transfer outside of the hospital. There is processing inside your hospital, as was quite well described, right? GDPR still holds. Federated learning is not a way to circumvent GDPR. But what we can say is that what is shared along the lines is outside of GDPR. It's anonymous data. It's not personal data anymore. And this works. And you see here you saw the accuracy, and I can't go back, I think, of that model. Oh yeah, thank you. So you see that the area on the curve of such models are actually much higher than doctors can do. So that's the idea. So now this has scaled globally, and we're doing more complex stuff, like federated deep learning, where you learn from a CT scan. Again, scans, images, as was just described, are extremely hard to anonymize. I don't think they can be anonymized, not anymore, at least not for the future. So rather than transferring data, we send the AI there that can find where the lung cancer is in this case. And we do this on a global scale, not just because you have more data then, that's important, but more importantly, you have diversity globally. You have Chinese people, you have Western people, you have black people, you have different CT scanners, and we're learning in AI from such diverse data, your AI will become more generalizable, i.e. more stable. And it can handle very different situations because it has seen very different situations. A machine learning model on AI is just as good as the data that it saw. And we do this amongst others. Leuven is one of our partners in this project. So we have decided to make everything open source because we know there are many companies involved in this. So we get these dashboards, which you also can do in Federate in the ATHENA project, I think. How do you then make data fair? How do you make sure that all those sites in the world or in your network adhere to the same model? So in the beginning, we thought that would be something like a worldwide common data model. And I think the Odyssey OMO community still has that dream. We have lost that dream about 10, 12 years ago. It's like saying everyone should speak the same language, should drive on the same side of the road, should use the same plugs. It will never happen. It will never happen. But we all use the same phone, EHR software. It will never happen. So rather than having this dream, we said, look, we're going to have a project-specific data model. So whenever we have a question, we know which data elements we need to answer that question. It is for those questions that we're going to make the data interoperable between those hospitals, rather than making all the data of the hospital interoperable, because that will be a never-ending story. And this is often misunderstood of federated learning. Federated learning is privacy-preserving because the data doesn't travel, sure, right? But more importantly, federated learning starts with the question. If you know the question, you know the data elements that you need, which means you can minimize the data that you need to ask hospitals. This is going to be proportional. You have the question to go to an ethical board. You have the research question to ask the patient for consent in the GDPR sense, because you start with a question. And that is important, because that makes our life way easier than thinking about, oh, let's do all this data and we'll figure out later what we'll do with it. This is not what we're doing. And so we use, for images, we use XNet, and sometimes we Odyssey or OMOP, and sometimes we do other stuff. So our current federated learning project that we run today are these 18. And you can see that they're on a wide variety of health cases, but also now in crime and in poverty. Because sensitive data is all over the place. And sharing data in federated learning is also interesting for the military, right? So we have this question now, how can we, NATO wants to do federated learning for intelligence, right? Or banks want to do this to detect fraud, which is an interesting way where, for the first time, I think, health did an IT development which was further along than all the other sectors. Yeah. So some example projects here is in rare cancer. So this is in anal cancer. What we managed to do with 3 sites is do 281 patients, and then we scaled up to 16 centers. Now we have 1,600 patients where we learn these machine learning models in. And this is by far the largest data set ever collected, well, not collected, shared in a federated sense on anal cancer. Final slide is the implementation of such models to choose which patient gets a very expensive therapy, like proton therapy. And it's also for multiple myeloma. Our health insurance companies are asking us, can we use such a system to choose which patient will get the expensive drug? So the way we do it is we learn an AI in the Netherlands, in a federated sense, that compares the new therapy, the expensive therapy, with the old therapy, will detect which patient really benefits from it, and then the computer says no, or the computer says yes. It's the first time in AI, rather than a doctor tells a patient what to do. Because doctors can't predict the outcome, so they can't choose which therapy is best. Okay. Open issues, and we talked about, so I'll stop here. Making data fair is still an issue, legal and governance. It's something that we understand. I think I've been partly become a lawyer. I think it's very solvable. It just needs a clear path. We do have different federated learning implementations, and we also don't know how to pay each other for data, because we can't sell data, and we don't know which data was used for which AI, and how that leads to IP. And finally, there's some more difficult situations, like suppose you have a European health data space as a station, it's one patient. How can you learn over one N is one in a privacy-preserving federated manner? It's an interesting question that we're working on. And with that, I leave you. Thank you for having me.